Alright, welcome to iChem Lesson 3 on isotopes and atomic mass. We spent the day talking about all of the different subatomic particles and the structure of the atom, and now we're going to learn about that last number we find on the periodic table and how we find it. First though, let's do a little bit of a review. We have our three different subatomic particles. We have our proton, our neutron, and our electron. For all intents and purposes of this class, we assume, or we say, that the proton and the neutron both have mass, which we approximate to 1 atomic mass unit, and we say that the electron has no mass. We approximate to 0 AMU. If you want to look real quick at the numbers, the mass of a neutron and the mass of electron, you can see that an electron is like a little over 1,000 times smaller than a neutron or proton in terms of mass, so that's why relatively we call it 0. The proton is found in the nucleus, so is the neutron, and the electron is found outside of the nucleus. Let's review the three important numbers we've talked about so far. We have atomic number, mass number, and atomic mass. Think real quick back, or flip over and look at your notes, which of these is displayed on the periodic table? Right, the atomic number we have here, and the atomic mass. So the atomic number is here, and the atomic mass is here. The mass number does not show up on the periodic table. What does each number tell us about the atom? Well, the atomic number tells us how many protons, the mass number tells us how many protons and neutrons, and the atomic mass, well, I'm not quite sure yet. We'll talk about that today. And how is each calculated? We don't need to calculate the atomic number. That will be given to us as long as we know the identity or the number of protons. The mass number we find by adding together the number of protons and the number of neutrons. And today we're going to learn about the atomic mass and how we calculate that. So first let's define an isotope. Take a look at these three isotopes of hydrogen. The first isotope here, you look at the nucleus, you have 1 proton. The atomic isotopic notation in this case then would be, we would have H for hydrogen, 1 proton as the atomic number, and if we wanted to calculate the atomic mass or the mass number, remember we do protons plus neutrons. There's 1 proton, no neutron, so it's 1. Let's look at the next one. Let's look at the next one here. We have 1 proton, 1 neutron. It's still hydrogen because it only has 1 proton. That's the atomic number and the identity, so this part stays the same. The part that changes now is the mass number. We have 1 proton, 1 neutron. Add them together, you get a mass number of 2. Last one, still hydrogen because I have 1 proton, but now I have 2 neutrons. 1 proton plus 2 neutrons, a mass number of 3. Remember our other form of isotopic notation, we have the name of the element and the mass number that goes with each of our isotopes. So why are all of these three considered to be hydrogen even though they're different? Remember that protons gives you atomic number, which gives you the identity. They all have the same number of protons, so they all have the same identity. They're all hydrogen. So what's different? Well, the neutrons. When the neutrons differ, it's considered to be an isotope. So the definition of an isotope: atoms of the same element, meaning the same number of protons, that have different masses because of different numbers of neutrons. Therefore, they have different mass numbers. So let's compare this. Just think of an analogy, and we'll work on another analogy tomorrow with candy. All the Legos in the box, all the blocks are called Legos, but they're not identical to each other. In the same way that all of these are called carbon, but they're not identical to each other. And all of these are called lithium, but they're not identical to each other. All of these are called helium, but they're not identical to each other. They're identical in their number of protons. They differ in their number of neutrons. Just like the Legos are identical in the idea that they, sort of all fit together, they have the same shape, but they have different sizes, number of holes, colors, but they're all Legos. Most elements have several isotopes. So where does this atomic mass come from? If there are 3 different types of magnesiums shown in the table below, which one is represented on the periodic table? Take a look at the masses of each of the isotopes. Take a look at the mass on the periodic table. Yeah, none of them. No single isotope is represented on the periodic table. That means no magnesium atom actually weighs the number represented on the periodic table. All of the different types of magnesiums were averaged. So how do you find that atomic mass? The atomic mass on the periodic table is an average of the masses of the isotopes of that element. The equation we use for that is right here. We use the decimal form of the abundance times the mass plus the decimal form of the next isotope's abundance times its mass, and so on until we do all of them. We'll talk more about what this idea of relative abundance is tomorrow, so let's just kind of practice, do a couple of applications of the equation. So for the first one, I have my relative abundance of 0.7870, and I want to multiply that by the mass, 23.985. And now my next one, 0.1013 times the mass of that isotope plus 0.1117 times the mass of that isotope. Before you plug this into your calculator, please get an idea of what the number should be. Look at all of the masses. Your number should be in between, in the range, fall in the range of all of these numbers. If you plug it into your calculator and you get something different than that, that means you made an error. Maybe in writing the equation, maybe in plugging into your calculator, but please do that. I am not lying to you when I tell you that on both of the example problems for these notes, the first time I plugged it in, I got the wrong answer. Maybe I'm bad with a calculator, but maybe some of you guys are too. The answer, when I plug all of this in, is 24.11 atomic units. All right, let's do one more. In this case, we're looking for the atomic mass of titanium. It's given to us in a slightly different way. I like working from a table, so I'm going to turn this information into a data table where I have mass, percent, and decimal. So the masses, I have 46, 47, 48, 49, and 50. I'm not outright given the masses of any of these, but the mass number, when necessary, is a pretty good approximation of the mass of each isotope, because remember, protons plus neutrons is the mass number, and a proton and a neutron are each approximately 1 atomic unit. Okay, now let's record the percents. I have 8%, I have 7.8%, I have 73.4%, I have 5.5%, and I have 5.3%. Look at the equation though. I don't want the percent form of the abundance. I want the decimal form. So if you're given percents, you need to change it to decimals, which means divide by 100, or move the decimal place over to the left 2 places. So 0.08, 0.078, 0.734, 0.0555, and 0.053. I want the decimal times the mass. So 0.08 times 46 plus 0.078 times 47 plus 0.734 times 48 plus 0.055 times 49. Last one, see if I can fit it, plus 0.053 times, to go up, 50. Okay, sorry for the messiness. I'm still getting used to using this silly pointer again this semester. So I multiply and add. Remember, get an idea of what you want the numbers to be before you plug them in. I need to be within this range. If I get something that's not between 46 and 50, I did something wrong. I plug it in. I get 47.93 AMU. We will definitely work more with this in class tomorrow. Make sure you complete the Google form. See you tomorrow.